All right, limits with radicals. Now you notice sometimes these problems will just be a radical by itself. Other times they'll be part of fractions. And obviously, as we've discovered so far, limits are usually harder when they're part of a big fraction, because that means they're probably indeterminate and you have to do some trick to it, right? So this video is just going to be about the trick to use when you have a radical in a giant fraction. Now I'll show you real quick that some of these won't require any trickery because, hey, we can just plug in numbers, right? The first thing we always do, even if there's a radical, is we plug in. Plug in 7 of this, it's not indeterminate, it's just the square root of 2. Because 7 minus 5 is 2, square root of 2. If we plug in 3 to this guy, we just get 9 minus 4 is 5, over square root of 9, which is 3. 5/3, we're done. No trickery required, right? So that's why whenever you have a limit problem, always plug in first. Something similar will happen. Here we'll get negative 3 squared is 9, 9 minus 6 is 3. Downstairs, oops, 0. All right, so this one, we're done, but what's the deal? Dividing by 0 is actually okay in a limit problem, right? All that means is the limit is infinity or does not exist. Depends what your teacher wants you to write as to how you would write that down. But the point is that 3 divided by 0 is not indeterminate, meaning that we'd have to do some more work or something. Like 0 over 0, there's more work to do. Got to factor or something. Infinity over infinity, indeterminate. We got to do some more work. But 3 divided by 0, or if it had been 0 divided by 3, just flipped over, either way on those two, we're done. It's just either 0 or infinity, whatever. You write it down and move on. All right, so there's only one trick for roots, basically, and that is rationalizing. So all the tricks you would use to rationalize denominators in the square roots, you're going to use when those roots have letters in them as well. If you want to go back to Algebra 2 and check out the roots and rationalizing denominators type chapter, just do a search on rationalizing denominators and you should come up with those videos. But the point is we're going to use some of the same trickery just with letters instead of numbers. So if you wanted to get rid of a root downstairs, what do? Well, just multiply by the root again, right? So x minus 2, got to multiply top and bottom by the same square root. Upstairs, we're just going to have x minus 2 is not, we can't really multiply that into the root, so let's be stuck with this. But downstairs, square root of x minus 2 times square root of x minus 2 just gives you x minus 2 without a root. So that's just a property of square root. It's like square root of 2 times square root of 2 would give you 2. Square root of x times square root of x just gives you x. And therefore, square root of x minus 2 times square root of x minus 2, same thing, equals x minus 2. That's how we got this. But what's wonderful, this problem was obviously contrived to just, oh look, they cancel. So now I had x minus 2 upstairs I started with. X minus 2 I just came up with downstairs reduces everything to square root of x minus 2. And that's something we just plug into, because we plug in 2 right here. Square root of 2 minus 2 is 0. Square root of 0, which is just 0. Now again, that's not indeterminate because it's not 0 divided by 0. As soon as this denominator canceled out, we no longer had a giant fraction we were working with. The problem is pretty much a done deal at that point. You just have to plug in. 0 is a fine answer. Infinity is a fine answer. It's just if you have 0 over 0 that you're in trouble and need to do some more work. All right, here's one that it doesn't look obvious, but actually we're going to rationalize this one just like we rationalized the denominator. The only trick is we're rationalizing the numerator. But the point is that to get rid of a root, you need to multiply by that root. So we're just going to multiply by root squared x minus 5, squared x minus 5. All right, so up top, square root of something times that same square root is just that thing. Oops, 5, not 3. And then downstairs we'll have x squared minus 25. All right, so at this point, hopefully you've seen enough math that you're like, huh, for one thing that x minus 5 didn't cancel, but right away when you first saw this problem, you might have been thinking to yourself, that's interesting, a difference of squares downstairs. I wonder if we should factor that. That is what we need to do, because right now this x minus 5 upstairs doesn't cancel. And if we just plug in 5, we'll still be indeterminate. We'll still have 0 over 0. But if we factor that downstairs, so we still have x minus 5 upstairs, but if we factor the downstairs and x plus 5 times x minus 5, and again, if you're not a factoring master, factoring whiz, check out the videos in the factoring chapter in Algebra 2 on this site, or Algebra 1. But point is, now we've got an x minus 5 we can cancel. Remember, you have to leave a 1 behind, because when we cancel that x minus 5, we're not left with 0 upstairs, we're left with a 1. Just like if you were reducing this fraction 2/4, that equals 1/2, not 0/2, right? So when you cancel that 2, you leave a 1 behind, because 2 goes in that once. So x minus 5 goes into x minus 5 once. That's really important, because otherwise you'll get 0, when in fact you should have gotten 1 divided by 5 minus 5, which is 0. All right, so we get undefined instead of 0. All right, so 1 over 0, as I've said many times now, this is not indeterminate. We're just done. So 1 divided by 0 is infinity, or does not exist, meaning the limit does not exist. And if your teacher was a stickler, maybe we should have written the limit as x approaches 5 in front of every single one of these steps. But hey, we're not going to rule like that, because that would be too crazy. Too much work. But you should do it. If you need to do that to get full credit, do whatever your teacher asks of you, Draw on the limit every time. All right, what if the radical is not by itself? Now this is the trickiest looking one, but again, this is something you occasionally came across in Algebra 2. Right now this thing is indeterminate because we plug in 3, we get 2 minus 2 is 0, and 3 minus 3 is 0, so we get 0 over 0 right now. But there's not really a sort of normal rationalizing situation because the root's not by itself. When you rationalize the denominator or something, those previous problems we looked at, we'd have the root all by itself, either downstairs or upstairs. But this one, it's blending in, right? It's got that minus 2. So we can't just multiply top and bottom by square root of x plus 1. That wouldn't help us. What we're going to do is multiply by what's called the conjugate. So we're going to take these same two numbers, and I'll just remind you, this came up in complex numbers. So if you had like, I don't know, 2 over 2 plus I, and you're supposed to rationalize this or whatever, what you would do is you would multiply by 2 minus I. And that was called the conjugate, where we just took the 2 plus I and made it 2 minus I. 2 minus I and 2 plus I are conjugates of each other. And the same thing is true here. Square root of x plus 1 minus 2, its conjugate is the same stuff, plus 2. And of course we can do that top and bottom, and we have to, even though it's not really going to help us downstairs, it'll help us upstairs. All right, so all I did was I took the same square root of x plus 1 minus 2, and I just rewrote it with a plus sign. So here's what's going to happen, and here's why that's so great. This is kind of like the factoring of squares. So now if we FOIL this stuff out, we get square root of x plus 1 times square root of x plus 1, which is just x plus 1. Then we'll get square root of x plus 1 times 2. But then we'll also get that same thing times negative 2. So those middle terms will cancel out. And then the last term is the only thing we keep, which is negative 2 times plus 2, which is minus 4. And then downstairs, we're not actually going to do anything with the downstairs. You could FOIL this out, but it turns out that would be a mistake, because look what this top turned into. X plus 1 minus 4 is actually x minus 3. Ooh, and where have I seen x minus 3 before? Right here in the original problem. It's downstairs. So if I leave that x plus minus 3 upstairs, and then downstairs, if I don't FOIL anything, if I just leave it x minus 3 times square root of x plus 1 plus 2, now my x minus 3 is still there to be canceled out. And again, we got to leave a 1 upstairs. So this is reduced, after all this work, and a giant mess, obviously, it's reduced to 1 over square root of x plus 1 plus 2. Now when I plug in 3, I get 1 over square root of 4 plus 2, which is 2 plus 2, which is 1/4. Pretty dandy. So this big mess that originally was indeterminate and gave us 0 over 0 has now given us a limit of 1/4. So you can see how zeros really aren't created equal, that 0 over 0 turned out to mean 1 over 4. Who would have guessed? All right, so as usual, first step is always to try plugging in. If you have a root, either multiply by the root itself if it's all alone, or if it's a root plus something or minus something, just multiply by the conjugate. Turn a plus sign into a minus, or a minus sign into a plus, but either way that root will magically cancel out when you FOIL those two big messes together.